In this chapter, you probably learned that velocity and acceleration can be broken into two parts. A few new equations are introduced as well. First, imagine there's a particle that's traveling along a path. From a fixed location, we can determine the position of the particle. That is called the radial coordinate, represented by the letter r. Another way to think about it is to think of r as the position equation. The fixed position is called the origin. If we have a fixed reference line, the angle the particle makes between that line and the radial coordinate is represented with the theta symbol. Theta is called the transverse coordinate. A theta symbol with a dot on top is called the angular velocity. It is the derivative of the angle with respect to time. A theta symbol with two dots on top is called the angular acceleration. That's the derivative of the angular velocity. R with a dot on top is the first derivative of the radial coordinate with respect to time. A second derivative of that is r with two dots on top. Velocity and acceleration can be broken into two parts. They are the radial component and the transverse component. For velocity, the equation for the radial component is this, and for the transverse component, we have this equation. The magnitude of velocity can be found using this equation. Another way of writing it is this. For acceleration, we also have three equations. The first is for the radial component. The next is for the transverse component. The magnitude of acceleration can be found using this equation. Another way of writing it is this. All of this will make more sense when we do examples. One thing to remember for this chapter is the chain rule from calculus when doing derivatives. It will become very handy. If you don't remember this section, there is a video in the description below that goes through how to do it. Let's go through some examples so that we can look at how to apply these equations. In this question, it's asking us to find the magnitudes of velocity and acceleration of the car. Let's write down what we know from the question. We're given the angular velocity, the angular acceleration, and the theta value at which we're trying to find the answers. And we see that r is equal to 200 meters. So one way to think about this is to realize that the car is 200 meters away from the origin, or its position is 200 meters away. Since it's a constant value, meaning the distance from the origin doesn't change, the first and second derivatives of the radius or position is 0. Now we can focus on the magnitude of velocity. Let's find the radial component of velocity using this equation. We already established that since r is a constant, the first time derivative is 0, so our radial component of velocity is 0. Now we can find the transverse component using this equation. Let's plug in the values we know and solve. Next, we can find the magnitude of velocity using this equation. Once again, we can substitute the values we know and solve. This gives us the magnitude of velocity. Now we can solve for the magnitude of acceleration. We will first find the radial component of acceleration. We will use this equation for that. Let's plug in the values we know. Now for the transverse component of acceleration. Again, let's plug in the values. Since we have both parts, we can find the magnitude using this equation. Solving gives us our answer. Let's look at another example. In this example, we are asked to find the angular velocity of the camera when theta equals 15 degrees. So as before, we will start by writing down what we know from the question. We know the magnitude of velocity, which is 40 meters per second. We also know the equation for the position. Notice how this equation is not a constant like the previous question. This means the distance from the origin to the car is changing with respect to the angle. We also know the theta value at which we're trying to find the answers. So this question is asking for the angular velocity. That means we will end up using our magnitude of velocity equation. We see that other than the angular velocity, which we are trying to find, we also need to have the first time derivative of our position equation. That's going to be our first step. You will need to remember the chain rule from calculus, which you definitely need for this chapter. So let's do the derivative of our position equation. Now we need to figure out the values of our equations when theta equals 15 degrees. So we can start plugging that value in. First, for the position equation. Next, for the time derivative of our position equation. Now that we have all the pieces, we just need to find the angular velocity using the magnitude of velocity equation. Let's plug in everything we know. Now we just need to solve for the angular velocity. Square both sides. Solving gives us our answer. Let's take a look at one last example. In this example, we need to determine the radial and transverse components of velocity and acceleration when theta equals pi over 3. Let's start by writing down what we know. We know the constant angular velocity, the position equation, and the theta value at which we are trying to find the answers at. This question asks us for the components of velocity and the acceleration. So that means 2 time derivatives must be taken of the equations. If it's only velocity, then you only need 1 derivative. But if acceleration is involved, you would need 2. You can actually see that from the equations of acceleration and velocity. So we will start with the first time derivative of our position equation. Remember, the position equation in this question is not a constant. Now, the second derivative. Now let's figure out the values when theta is equal to pi over 3. Next, we will use the angular velocity given in the question to figure out the first time derivative value of our position equation. Now to calculate the second time derivative of our position equation, we need the angular acceleration. But you will notice that our angular velocity is actually a constant. That means taking the derivative tells us that the angular acceleration is 0. So the value of our second time derivative of our position equation is 0. Now that we have all the values, we can find the radial and transverse components. We will start with velocity. The radial component of velocity is found using this equation. Next, the transverse component of velocity is found using this equation. We're just plugging in values and solving. Now for the acceleration components. First, the radial acceleration, which can be found using this equation. Plug in what we know and solve. Next, the transverse component, and the equation for that is this. Let's substitute the values we know and solve. Those are our answers. Lastly, be careful when taking time derivatives. It's usually an easy place to make a mistake. Thanks so much for watching, and I hope this helped. Best of luck with your studies.